Welcome back to Calculus 1. In Chapter 1, we used limits to describe what happens to a function as the input approaches a particular value. We now begin Chapter 2 and use limits for a new purpose, finding how steep a curve is at one particular point. We will begin with slopes between 2 points and then bring those 2 points closer together. The limit of those slopes gives the slope of the tangent line. Finding that slope at different inputs creates a new function called the derivative. This is where the limit ideas from Chapter 1 become the foundation of differential calculus. Let's get started. Here's what we will cover in this lesson. First, we will see how a tangent line is obtained from secant lines through 2 points on a curve. Next, we will use a difference quotient and a limit to find the slope of a curve at one point. We will then allow the point to vary, producing a new function called the derivative. Finally, we will connect differentiability with continuity and identify several common places where a derivative fails to exist. One question drives the entire lesson. What happens to the slope between 2 points as those points get closer and closer? Here's a tangent line problem. A tangent line passes through a chosen point on a curve. Its slope tells us whether the curve is rising, falling, or level at that point, and how steeply. To find this line, choose a second point on the curve and draw the line through both points. That line is called a secant line. Now move the second point towards the first. Each new position produces a new secant line and a new secant slope. If the secant line settles towards one particular line, that limiting line is the tangent line. Its slope is a number the secant slope approaches. The tangent line problem is therefore a limit problem. What number do the secant slopes approach as the second point moves towards the first? The slope of a secant line. Let's begin at the first point on the curve. Its input is c, and its output is f of c. Move horizontally by an amount called delta x to reach a second input. Because the second input is also on the curve, its output is determined by the function. The horizontal change between the points is delta x. The vertical change is the difference between the two output values. Dividing the vertical change by the horizontal change gives the slope of the secant line. This ratio is called the difference quotient. Remember that delta x is one symbol representing a change in the input. It is not delta times x. For a secant line, delta x does not equal 0 because 2 points must be different. We will keep it non-zero while allowing delta x to approach 0. Let's define the tangent line. As the second point moves towards the first, delta x approaches 0 and the secant slope changes. The limit asks whether those secant slopes approach one particular finite number. If they approach a finite number m, then m is the slope of the tangent line. The tangent line passes through the original point and has slope m. We do not set delta x equal to 0 in the difference quotient. That would place 0 in the denominator. Instead, we use non-zero values that become smaller and smaller. If the secant slopes do not approach one finite number, then the graph has no tangent line with a finite slope at that point. It may have no tangent line there, or it may have a vertical tangent whose slope is undefined. Let's look at an example. Let's apply the definition to the quadratic function f of x equals x squared minus 6x. After substituting c plus delta x, expanding and simplifying, the secant slope becomes 2c plus delta x minus 6. As delta x approaches 0, the delta x term disappears. The tangent slope at input c is therefore 2c minus 6. This formula produces different slopes at different points. At c equal to 1, the slope is minus 4. so the curve is falling. At c equals 3, the slope is 0, so the tangent line is horizontal at the vertex. At c equals 4, the slope is 2, so the curve is rising. The graph makes the main idea visible. The slope of a curved graph changes from point to point. Let's talk about the derivative of a function. On the previous slide, the formula 2c minus 6 returned the tangent slope for any chosen value of c. A rule that takes an input and returns a tangent slope at that input is itself a function. We call this new function the derivative. In the definition shown here, x represents whichever input we choose. At each x where the limit exists, f prime of x gives the slope of the tangent line at the corresponding point on the graph. The derivative also gives the instantaneous rate of change, that is, the rate at which the output is changing at that exact input, rather than across an interval. You will see several equivalent notations, including f prime of x, y prime, and dy over dx. They all refer to the derivative. This is the same limit used for one tangent slope. The difference is that the input may now vary, so the resulting slopes form a new function. Let's work through the steps. Let's use the limit definition to find the derivative of the cubic function f of x cubed minus 5x. Begin with the difference quotient. After expanding and subtracting the original function, every remaining term in the numerator contains a factor of delta x. Dividing every term by delta x before taking the limit. Divide every term by delta x before taking the limit. If we substitute 0 too early, we obtain 0 over 0. As we learned in chapter 1, that is a signal to simplify. It is not an answer. After the cancellation, the terms that still contain delta x approach 0. The derivative is 3x squared minus 5. The process is consistent. Set up the difference quotient, simplify it, and then let the change in the input approach 0. Let's do an example. The square root function requires a different algebraic step. Its difference quotient contains a difference of 2 square roots in the numerator, so there is no common factor to cancel immediately. Multiply the sum of those roots over itself. This factor equals 1, so it does not change the value of the expression. It is also called the conjugate factor. The product turns the numerator into delta x. After the factor cancels, we can take the limit. The derivative is 1 over 2 times the square root of x plus 4, for x greater than negative 4. At x equal to 0, the tangent slope is 1/4. At x equal to 5, it is 1/6. The smaller slope at x equals 5 shows that the curve is still rising, but it is becoming less steep. The algebra changed, but the limit process remained the same. Here's another example. Another variable and the tangent line. The input variable does not have to be x. In this example, the input is t, so the small change is written as delta t. The two fractions in the numerator need a common denominator. After combining them, a factor of delta t appears and cancels. Taking the limit gives a derivative negative 6 over t squared, for t not equal to 0. At t equals 2, the function value is 3, so the point of tangency is 2, 3. The derivative at t equals 2 is negative 3/2, which is the tangent slope. Using that point and slope, the tangent line can be written in point-slope form. After simplifying, its equation is v equals negative 3/2 t plus 6. The letters may change, but the structure of the derivative process does not. Now it's your turn. The first two problems ask for the slope at a particular point. The last two ask for the derivative as a function. For the first two, simplify the difference quotient and then substitute the given value of c. For the last two, keep x as the input so that your answer is a derivative function. Use a limit definition from this lesson. The shorter differentiation rules will come next. Pause the video now and work all four problems. When you are ready, come back to check your answers. Let's check the answers. For problem 1, the slope is -2. The difference quotient is already -2 because a straight line has the same slope everywhere. For problem 2, the derivative is 2x plus 2. At x equals -1, the slope is 0. So the tangent line is horizontal at the vertex of the parabola. For problem 3, the derivative is 8x minus 1. For problem 4, the derivative is 1 over 2 times the square root of x minus 1 for x greater than 1. At x is equal to 1, the secant slopes from the right increase without bound, so there is no finite derivative there. Although these functions look different, every answer came from the same limit definition. Only the algebra used to simplify the difference quotient changed. Differentiability and continuity. We will now connect differentiability with continuity. If a function is differentiable at a point, then it must be continuous at that point. In other words, the existence of a derivative guarantees continuity. A break in the graph prevents the nearby secant slopes from approaching one finite number, so a derivative cannot exist at a point where the function is not continuous. The reverse statement is false. Continuity does not guarantee a derivative. A graph can remain unbroken and still have a sharp corner or a vertical tangent. Therefore, continuity is necessary for differentiability, but continuity alone is not enough. Three common ways a derivative can fail to exist. The three graphs on this slide show common reasons a derivative can fail to exist. At a sharp corner, the secant slopes from left and right approach different values. Because there is no single limiting slope, there is no derivative at the corner. At a vertical tangent, the secant slope grows without bound. The tangent line is vertical and the vertical line has an undefined slope. Therefore, the derivative does not exist there as a finite number. At a break in the graph, the function is not continuous. Since differentiability requires continuity, a derivative cannot exist at the break. The first two graphs can be continuous at the mark point even though they are not differentiable there. The graph with a break is neither continuous nor differentiable at that point. Let's bring the main ideas together. A secant line passes through 2 points on a curve. As a second point approaches the first, the secant slopes may approach one finite number. That number is the slope of the tangent line. The difference quotient calculates each secant slope, and its limit gives the tangent slope. When we repeat the process for different inputs, the resulting slopes form a derivative function. Wherever it exists, the derivative gives both the tangent slope and the instantaneous rate of change. A finite derivative can fail to exist at a sharp corner, a vertical tangent, or a break in the graph. Differentiability implies continuity, but continuity does not imply differentiability. In the next lesson, we will develop differentiation rules that produce these same derivatives without repeating the complete limit process each time. Thank you for watching. In this lesson, we began with slopes between 2 points and used a limit to find the slope at one point. That limiting slope belongs to the tangent line, and finding it at different inputs produces a derivative function. We also connected differentiability with continuity and identified 3 common reasons a derivative may fail to exist. In the next lesson, we will introduce the basic differentiation rules and apply derivatives to rates of change. I'll see you there.